Hello students, welcome to Young Ups. In this part of Forces and Energy, which is part 3, we shall be talking a lot about heat or thermal energy and temperature. Let's start. Okay, so when we talk about heat, the other name for heat is thermal energy. Okay, so we always knew that heat is a kind of energy. Okay, and when heat is applied to any particle or any object, what exactly happens? Okay, it gets, first of all, try and understand, children, that the heat energy can be absorbed by any particle, so it can be transferred to objects, and then the object, if readily transfers it, okay, then it is called as the conductor of heat. But if it does not readily accept the heat, see, heat anyhow gets transferred, but if it does not dissipate in large amounts, then that object is known as an insulator. Okay, so thermal energy can be stored in an object. How does it get stored in an object? The object absorbs it. Okay, but the thermal energy that is stored will eventually dissipate in the surrounding. So forever something will not remain hot, it will cool down. How does it cool down? The heat energy will move or spread out in the surrounding air. Okay, if it gets transferred or to an object, if it gets absorbed by the object, eventually, there is an exchange with the environment, heat energy will move out and the object will again cool down. Okay, thermal energy is measured in joules. When the thermal energy of any object increases, the particles in the object start to vibrate faster. And that's the reason why, children, there is a state of matter. There are these states of matters. Okay, solid particles, when vibrate really hard, they break the intermolecular forces of attraction and turn into a liquid. We've studied that. Okay, so heat or thermal energy can change the state of matter from solid to liquid and from liquid to gas. Similarly, when the heat energy or thermal energy is lost, or if it gets dissipated into the surrounding, okay, it loses energy and a gas can turn back or get converted into a liquid, and the liquid get converted back into solids. The energy, as you know, again stated, is measured in joules. Heat is a measure of the energy in the particles. How can heat be measured? It is how hard the particles vibrate. Okay, it's the energy of the particles. Okay, how fast they start moving or how fast they start breaking the intermolecular forces of attraction between them. Heat is the total thermal energy of the vibrating. So this is the definition of heat. Okay, heat is nothing but the total thermal energy of the vibrating particles in an object. So let me repeat it. Heat is the total thermal energy of the vibrating particles in an object. Very simple, children. Very easy to learn. Say it 5 times and the definition goes right into your brain. Okay, now look at this. Okay, we have two glasses and both the glasses have the same amount or the same ml of water in them. But what is the difference between them? One glass has water which is at room temperature, and the other glass has water at a higher temperature. Okay, so the volume of water is the same in both glasses. One has a higher temperature than the other. meaning that the thermal energy of the one which is hotter is greater, right? The water at the higher temperature contains more vibrating particles, correct? Okay, so how will heat be measured? If the heat will be measured by the by how much energy the particles have to vibrate. Okay, the number of particles in both the glasses of water is the same. Number of particles in both the glasses is the same. But the total thermal energy, okay, is more. The energy of those particles is more, which is hotter, right? So if A is at room temperature and B is hotter, that means B has more energy, more thermal energy in it. Okay, now let's change this a little. Let's change the scenario a little bit. We have glass A here and we have glass B here. Okay, what exactly is the scene now? In glass A there is more water, in glass B there is less water. However, glass A is at room temperature, okay, and glass B is the water is hot. It has, so that means it has more thermal energy. So the water in glass B, since it's hot, has more thermal energy, and hence the particles, okay, will have a greater energy than that of glass A, though it has fewer particles. Okay, so that means that the larger volume of water has greater thermal energy. Okay, okay, so this one has the lesser one will have greater thermal energy because it has a higher temperature. Let's read the text. The water in both the glasses is at the same temperature. Okay, it has the same temperature. There is a larger volume of water in one glass, so it has more particles. As there are more particles, in case if we heat up this glass, that means it will have more energy. More particles will carry more thermal energy. Yes, less particles will carry lesser thermal energy. Here, if this is at room temperature, okay, but the particles are more, okay, it will not have that much of energy. So that means the larger volume of water, if it has greater thermal energy, more thermal energy than the smaller volume, this glass, more particles, more energy it can hold within itself. The particles, more of the particles are vibrating. Okay. Now, what is temperature, children? Temperature is how you measure heat. Okay. Temperature and heat are not the same. Temperature gives us information about two things. One, in which direction is the thermal energy transferred. So, if I have particles out here, okay, if they are vibrating, okay, this also starts vibrating, and so does this. So, the energy is getting transferred in this direction. Yes, and then if this one has say 100 joules, just an example, this one has 50 joules and this one has 25 joules, so an average of all the three will be removed, will be taken, okay, and then it gives us the average energy of the particles in the object. So it's the average. So what does the temperature tell us? The direction in which the thermal energy will be transferred and the average energy of the particles. Okay, I'll repeat. Temperature tells us the direction that thermal energy will be transferred in, and it tells us the average energy of the particles. Now, we have this ice cream in this picture. Yes. Now, children, this ice cream has a low temperature. Okay, it was frozen at about somewhere around minus 20 degrees Celsius. Okay, and what is the room temperature? Okay, approximately 24 degrees Celsius. So, the thermal energy is transferred from the air to the ice cream simply because the air is comparatively hotter. If it's comparatively hotter, that means it has more thermal energy as compared to the ice cream. Correct. The particles in the air are vibrating faster than that of the ice cream. Correct, because of the now. So if you have to calculate which is a temperature, so the ice cream has been taken from a freezer at minus 20 degrees Celsius. The air in the room is at 24 degrees Celsius, which is a temperature. What is the temperature difference? Minus 20, okay, minus 40, minus 24. What is the difference? 44 degrees. Yes, 44 degrees Celsius is the difference. If you do it on a number line, okay, if I make a number line, I am at I am at 24 degrees, assuming this is 0, and here it is minus 20 degrees. So from 24 to 0 is 24. From 0 to 20, it is 20. So 20 plus 24 gives me a difference of 44 degrees. So the difference in the temperature of both of them is 44 degrees. Okay, so the higher the difference, the faster the higher the difference of the two the between the two objects, or between the surroundings, or yeah, basically between the surrounding air and the ice cream, the higher the temperature. Okay, so the larger a temperature difference between the two objects, the faster the thermal energy transfer. Had it been 0 degrees and 24 degrees, okay, thermal energy wouldn't transfer faster as compared to as compared to minus 20 to 24. So the more the difference, the faster the thermal energy transfer. I hope you understood what I'm trying to say. Okay, the temperature also gives us information about the energy of the particles, like we just discussed, the direction in which the energy is flowing. So if I have a glass, okay, which has hot water, okay, so here on the sides, the energy is dissipating. It is dissipate here. From the surface as well, the heat will be released. Yes, so the temperature tells us the direction, and it gives us the information about the energy levels of a particle. That's the reason why, see, these water molecules are changing to gas molecules. He tells us about the total energy of the particles. Temperature tells us the average. Remember, average, overall energy. This means that temperature is a good way of comparing the particle energy between objects of different sizes or made from different materials. So, what do we understand by this statement? It is difference in size. So, it basically means that if an object is bigger in size, it will have more thermal energy as compared to an object which is smaller in size. Okay, some materials, something like steel, or iron or any kind of metal will hold more heat energy, will be a good conductor of heat as compared to wood or any other plastic or any kind of material which does not hold the heat in it. Yes, so temperature also tells us, okay, is a good way to compare the heat energy absorbed or held by a particle. Okay. Now look at the picture of the hot soup and cold water. Okay, this is the hot soup. Okay, and this is the cold water. Okay, now the soup and the water in the picture are made from different materials. Yes, so the type of particles are different. Yes, the mass and volume of soup and water is also different. So if soup is more, it will have more thermal energy because it has more particles. When we say the temperature of the soup is higher than the temperature of water, we mean that the average energy of soup particles is higher than that of average energy of the water particles. Understanding, children? Another way to think of this is that 100 particles in a soup may have more energy than 100 particles of water because soup, a different material, has the capacity to hold or absorb more thermal energy. Now, heat and temperature in a sparkler. Okay, children, we know that fire has a very high temperature. Okay, but if you see a sparkler, it has very tiny sparkles coming out of it. Yes, it has very tiny sparkles coming out of it. Okay, when we, during Diwali, when we just move around or sway the sparkler in the air, many a times the sparkle particles, the sparkle particles come and touch our skin. Why don't we get a burn at that point? Let's read and find out. A sparkler is a small handheld firework. When you hold a sparkler, some of these sparkles may fall over your hand. The sparkler can be at a temperature of about 1000 degrees Celsius. But one spark does not cause a serious burn. Why not? The reason is the mass of the spark is very small. The amount of heat that it is holding, that small speck holding, is very small. And the temperature difference between the air and the spark is very large. Yes, children, so it flows out easily. The heat difference or the temperature, okay, by the time it touches our hand, okay, it's already lost into the surrounding air. As there are fewer particles in the spark than in the main part of the sparkler, the total particle energy is smaller. So if you have this as a sparkler, okay, if you touch the and it's sparkling, okay, it's sparkling. Okay, if you touch over here, obviously you will get a burn because of the amount of heat energy out there, the amount of particles which are concentrated out there. But over here, at the tips, when they are falling out, the particle size is smaller. Okay, when the particle size is smaller, the surrounding, it quickly moves out to maintain the temperature difference. And so if you're holding it, okay, if you're holding the sparkler, okay, it so happens that it's already moved out, the heat is already dissipated in the atmosphere, and so you do not feel hot for that matter, or you do not burn your hand. So as there are fewer particles in the sparkler than the main part of the sparkler, the total particle energy is much smaller. Therefore, the total thermal energy or heat of the spark is very small. As the temperature difference between the spark and the air is large, thermal energy will be transferred from the spark to the air quickly. Yes, in the short time the spark takes to fall to your skin, its temperature by the time has already dispersed in the air. Okay, and the heat have both decreased significantly. Yes, clear children. Let's have a differentiation chart between heat and temperature. Okay, so what is heat? It is a form of energy. Energy. What is temperature? It is a measure of hotness or coldness. Okay, heat is measured in joules and calories. Temperature is Celsius, Kelvin, or Fahrenheit. Heat is positive. Temperature can be positive and negative both. The temperature can go down as -20, -40, but heat will always be a positive number, a positive magnitude. Okay, always it's the heat which goes from hot to cold. Okay, however, when it comes to temperature, it rises when heat falls when cooled. Okay, so it's again remember, temperature is only a measure. How do you measure heat? The instrument or device is a calorimeter, whereas when it comes to temperature, it's always a thermometer. Hope you understand this much. Now, talking about energy. Energy, remember one thing, children, there is a law. Energy can never be created nor be destroyed. It can only change its form from one to the other. Okay? Or it can be transferred. Okay, so that's the law of conservation of energy. The amount of energy in the world, in the universe, will always remain the same. People often talk about conserving energy when they mean using less energy. For example, you switch off a lamp when you leave the room, so you're saving electric energy. In physics, saying that energy is conserved means something different than you say using less of energy. When we say that energy is conserved in physics, we mean that the total quality of energy stays the same. This happens when energy is stored, like potential energy. The energy is changed, it changes form from electric energy, it may turn to light energy or sound energy or mechanical energy. Energy can also be transferred between objects. Okay, or for that matter it dissipates in the surrounding. But energy, using less energy, okay, is different from that what we talk in physics. The amount of energy in the universe remains the same. So look at this diagram here. Okay, it says it has 100% chemical energy in fuel. Okay, out of this, how does energy get distributed? First, let's read the text. In the energy diagram for a car engine or car will always work on fuel, and fuel is chemical energy. Okay, the energy input and output are shown. Lot of spelling errors. Okay, and outputs are shown as percentages. Notice that the energy input is 100. Okay, as the total energy output adds up to 100. So this will always be equal to this. So input will always be equal to the output. Okay, once again, energy is conserved or utilized to the maximum for a particular job or a task. In these examples, the electric, so I'll go to this statement later. Okay, so there's 100% chemical energy in the fuel tank. Okay, only 25%. Children, only 20. This is output. I'll write it here. Output. Okay, only 25% out of the 100% is utilized for the car to move. Okay, we are left with 75%, out of which the car heats up, it makes a moving noise, so it changes to 35% is used up in as given out as heat energy and sound energy. Every car makes a sound. Okay, and then the 40% of chemical energy is in the exhaust gas. It's given out through the exhaust. Add it up, children, you will realize that input is equal to output. Okay, always. There's never there that I put in 100% but output is only 90%. No. Okay, that brings me to a concept of efficiency of a particular appliance. For example, take a bulb. Okay, a light bulb. Okay, now what is the function of the light bulb? To give out light. Okay, it will give out light. But after some time, if you go, just even bring your hand closer to the light bulb, you realize that it is so hot. So much of amount of energy has been given out as thermal energy or heat energy. So this thermal energy for a light bulb is actually a waste. So is my light bulb 100% efficient? Does my light bulb show me 100% efficiency? No. Yes, let's look at a washing machine in a house. When you look at a washing machine, what is the main job of a washing machine? You have to make sure the job of a washing machine is to make sure that the motor is having kinetic energy. So energy is used as kinetic energy. Energy is given up as sound energy, the sound or the amount of noise that a machine makes. And energy is also given out in terms of heat energy or thermal energy. Yes, but for that matter, sound energy and thermal energy are not required. They go as waste for the job. Okay, so my washing machine is not 100% efficient. Understanding, children? On the other hand, if you look at an iron, okay, an iron, the press that you use to iron clothes, okay, what is its job? To heat up so that the clothes can be ironed. Yes, children. However, what exactly happens out here? Heat is given out or thermal energy is given out. That is what it is for. Does it give out any kind of noise or any kind of sound? Yes, it may, but it is minimalistic. Okay, does it give out any kind of light? Yes, it does. That small little light, that shows that the iron is on. It gives out light energy also, but then it is not too much. Sound is also not too much. So thermal energy is at the maximum or most. So an iron apparently is quite efficient. My appliance is quite efficient for that matter. Okay. Now, in these examples, the electric lamp and the car engine are types of system. In physics, a system is something that has been chosen to be studied, especially in terms of energy changes. How the energy, light energy changed to heat energy, or heat energy changed to something else, is what it is. It helps us to study. The system helps us to study energy changes. Let's read. See, I told you energy. Read this, what's there in the picture. Here, energy cannot be created or destroyed. It can only be changed from one form to another. And the great Albert Einstein is the one who made this historical statement. So true. Okay, the total energy output can never be greater than the total energy input. If I have 100 particles of something, will I get 110 particles of that thing? No. It will always be, it can never be, this can never be more than this. The output can never be more than the input. This is because energy cannot be created. In the reaction, in the process, energy cannot be created. Created means to make something or to bring something into existence. Suddenly, energy increases. No, what is given in will stay, will remain. Nothing can increase or nothing new can be introduced into the system. Wasted energy, such as thermal energy, is dissipated. Okay, dissipated means that energy spreads out into the surrounding and becomes less useful. I just gave the example of washing machine or a light bulb. Although this energy is dissipated, it is not destroyed. It is gone into the surrounding. Destroyed is the opposite of created. Destroyed means to damage something or to end its existence. And that never happens with energy. The law of conservation of energy states that energy cannot be created or destroyed. It only changed or transferred. So what is the law of conservation? Is this exact statement stated by Albert Einstein. Very important, children. Okay. Now, always remember the movement will always be from hot to cold, because the heat gets into a particle, gets into the object. The particles vibrate and transfer the energy. Cold is not an energy. Okay, so feeling heat. When you put your hands around a hot drink, you can feel the heat. That means the heat is getting transferred to your hand. Your cold is not getting transferred to the cup or the mug. Okay, the heat or the mug is transferring the heat, okay, in your hands. This will only happen if the drink is hotter than your hands. Similarly, if I have a cold drink, okay, it is not that if this glass is a cold drink, I have ice in it, okay, and I clench my hands around it, okay, it is my hands. I don't know how to draw a hand. Okay, these are my hands which will, oh, not bad. Okay, these are my hands, okay, which are hot, so they will transfer their heat into the glass. So remember, it is always the heat that travels to a colder area. Hotter means at a higher temperature. Thermal energy moves from the drink through the container into your hands. And if the drink is colder, then the heat is transferred from my hand to the container and from the container into the drink. Okay? Now, thermal energy always moves from hotter places to colder places. Colder means at a lower temperature. We make use of this in many ways. When you put food into a refrigerator, so the thermal energy is being pulled out, okay, pulled out of the refrigerator, and the trans and thermal energy transfers out of, children, moves out of, transfers out of the food, and the food becomes colder. Now, there is water inside a car engine. To remove thermal energy from the metal engine, this stops the engine from overheating. So, this is fuming. Okay, a lot of heat is being given out, and this water is comparatively colder. For that matter, it is at room temperature. So, when we pour this water into the hot engine, the heat energy is getting transferred into the water. Okay, thus until when the both of them are at equilibrium, the temperature of the water and the engine come up to a temperature which is the same for both. Okay, it will come to an equilibrium, and the engine will cool down, the water will heat up, and they will be at the same level. Animals sometimes go in water to cool down. That means they have a lot of heat coming out. So, what are they basically doing? They are transferring their heat into the water, and when they lose the heat, they feel cold, they feel good. Thermal energy moves from the animal's body into the cold water. Hope you've understood the law of conservation, children. Hope you've understood that heat moves or travels through the different particles, and hope you've understood how matter exchanges its shape, its how states of matter changes. It moves from solid to liquid. Hope this much is clear, children. That's all for today. Thank you, and God bless you all.